Hey team, chemistry coach coming at you. Our last and final video, 8 in our atom atomic theory journey. This actually overlaps into compounds, right? We're going to do a whole journey on just compounds. So this is kind of a bridge between atoms and compounds. Molar mass, possibly the most common thing you're going to calculate is the molar mass of a substance. We're going to use it as a conversion factor. So let's compare and contrast what we've already known and what we're going to do now because we introduced the concept of the mole. Very important. So atomic mass, we showed you how to calculate average statistically weighted atomic masses with isotopic masses and fractional abundances and all that fun stuff. And that is the mass of a single atom. And we can't, since it's so light, it's like 10 to the minus 23rd and minus 24th grams. That's too light. We use units of AMUs, or atomic mass units. So what would be the mass of a single atom of an isotope, or an average, an average atom of an element if you look at all the isotopes? So that would be units of atomic mass units per atom, or just that mu symbol, right? So we can use that as a conversion factor to go from one atom to a mass unit of AMUs, which you could convert to grams if you wanted to, or tons, or whatever mass unit you want. Molecular mass is exactly the same idea, but it's the mass of a single molecule, which is multiple atoms combined together. Also in atomic mass units, because that molecule, one molecule of water is going to be pretty darn light, right? Good luck getting one molecule of water out of that. Boy, look, I got one molecule of water. Not going to happen. It's going to be really light. Right? But that would be units of atomic mass units per molecule, or that mu symbol, or Dalton's you'll see as well. So the new concept we're after, because we're not going to be dealing in lab ever with single atoms or single molecules or single ions, so we're going to be dealing with mole quantity. Remember, 1 mole of water. Perfect amount right there, about 18 milliliters. So we're going to be using the molar mass, right? What's the mass of 1 mole? Exactly 1 mole. And that will be no longer, now atomic mass units would not be a proper unit anymore. It'd be like weighing yourself in nanograms or something. That'd just be silly, or ounces. How many ounces do you weigh? Pounds or kilograms is a better unit. So if you're weighing mole quantities, the best unit is grams, which is what we weigh on balances. That's why we love this so much. Mole quantities are perfect. So the units for molar mass would be grams per mole. Now, because of the definition of a mole, the number you use, numerical value, so like carbon is 12.011, the value on the periodic table, right? So if I had a single carbon atom, on average, it would be 12.011 atomic mass units per atom. But if I had a mole of carbon atoms, it would be 12.011 grams per mole of carbon. The number stays the same. The number you find on the periodic table, if you're dealing with elements, stays the same, whether you're atomic mass units per atom or grams per mole. It's a wonderful thing. But this applies for any species. This could be for atoms. This could be for molecules, polyatomic ions. It doesn't matter what. It's just the molar mass of anything. So it's more of a generic term. A lot of people mix and match atomic mass and molar mass, right? So they'll say atomic mass, but they have the assumption that it's 1 mole of it. So technically not correct, but so commonly abused in the language of chemists, people just let it slide. But technically, if you say atomic mass, it's units of atomic mass units per atom. And if you say molar mass, it's grams per mole. But most people say molar mass for compounds and polyatomic ions, and atomic mass for elements. See what I'm saying? Technically not correct, but it's just a verbiage thing. Everybody does it, so it's not a big deal. All right, let's get into some examples for this puppy. Yay! And show you how to calculate them. All right, see if you can punch this out on your trusty calculator. We're going to need our periodic table now. Oh, let me get my thing off there. So grab your periodic table. Boop, boop. All right, so these numbers are AMUs per atom, or grams per mole of those atoms. Exactly the same number. So how many moles of barium are in 3.27 grams of barium? Going to be a very, very common calculation, taking a mass measured in a laboratory on a balance, converting it to moles, and then applying that to a balanced chemical equation. We'll find out relates different species by moles. Very, very common, if not the most common calculation you're going to do. So we're solving for moles and starting with grams. So we're going to go from grams of barium to moles of barium. Very simple. You don't have to put down the game plan for a one-step thing. It's pretty straightforward. But I could have started in nanograms or pounds or something, and you just got to get to grams to get to moles by definition. So here we go. Let's do this. We got 3.27 grams. And since it's in grams, we can go to moles directly using molar mass. So we want to know how many grams of barium there are per mole of barium so that the grams of barium cancel out. See that? So as long as you use unit line equations, you don't have to worry about it. You should never ask me, do I divide by the molar mass or multiply by the molar mass? That tells me you're thinking like a mathematician, which is not how we do it in chemistry. Chemists think differently because we have to worry about units and uncertainty, right? So it's math on steroids pretty much. So don't ever think of it that way. Don't go, do I divide by it or multiply? Go look at the unit, and I need to cancel the unit. And then the math falls in place. The division or multiplication just falls in place in order to cancel the units properly. So let's look up barium. So if I had 1 mole of barium, that's an alkaline earth metal, right? So if I had 1 mole of barium atoms, it would weigh 137.33 grams. If I had 1 atom of barium, it would be 137.33 atomic mass units, but we're dealing with mole quantity. So let's put 137.33 in there. And remember, molar masses, atomic masses are not exact. Only the value for the carbon-12 isotope, which is defined, is exact. All the other ones are not. All right, so I got 3 significant digits there, 5 there. I'm dividing, so I'm limited to 3 significant digits. And I get 0.0238 vertical dash line 11. There's our 3 sig figs. Use a vertical dash line, carry 2 more past it, or more if you want to do more. That would be moles. That's not going to round up, correct? So that'd be 0.0238 moles of barium. And then I could use this number in some other calculation. We don't normally just stop at moles. Let's do another calculation and advance it a little bit. This one might be a little more challenging. Not a simple one-stepper, but it uses the concept of molar mass, and we're still dealing with just with elements. When we get to compounds, we're going to have to figure out how to calculate those. All right, how many atoms of antimony are there in 42 milligrams of antimony? Right? So we're starting with milligrams. We've got to get to atoms. So let's think about a game plan here. So we're starting with milligrams of antimony, and we want to get to atoms. Right, so here's our starting point. Here's our ending point. Now, I can't go mass to atoms directly. I've got to go to the hub, moles. You've got to get to moles first. So I need, now to get to moles, I need this in grams, right? Because it's a molar mass is grams per mole. So if I can get to grams of antimony, right, 1,000 milligrams per gram, knowing I would expect you to have memorized that metric conversion. Once I'm in grams of antimony, I can get my periodic table and get to moles of antimony, and then moles of antimony to atoms would be Avogadro's number. Now, there's a symbol for Avogadro's number, by the way. It's called capital N, little a. That's a symbol for Avogadro's constant, technically, the 6.022 times 10 to the 23rd antimony atoms per mole of antimony. From here to here, we're going to use molar mass. From here to here, we're going to use the metric system. I'll put that below just to be consistent. And that is Avogadro's constant. Stretch the back. Amadeo Avogadro, and there's a lot of other names in there. Our Italian friend. So I recommend you pause this and work this out. Give it a shot. What do we got? 42 milligrams of antimony. Let's convert milligrams to grams. 1,000 milligrams per gram. Don't technically need to put antimony on here because everything's antimony. But I want you to get in the habit, whenever you write moles, tell me of what. Because it'd be like saying, hey, Dr. Lotz, I've got 2 dozen. And I'd look at you really weird. That doesn't mean anything. 2 dozen what? 2 dozen bowling balls? 2 dozen parking tickets? It's meaningless. So when you come to me in lab and say, Dr. Lotz, I need 2 moles. I look at you the same way, like you're weird or something. It's like, are you cray cray? What's going on? 2 moles is meaningless. 2 moles of what? 2 moles of iron? 2 moles of pickles? 2 mole? What are you talking about? I don't know. So please get in the habit whenever you write moles, moles of what? Just like dozen of what? Dozen by itself doesn't tell us anything. All right, check. Now let's go from grams to moles. So we want to know how many grams of antimony there are per mole of antimony. We need our trusty dusty molar mass. So let's find antimony. Hardest part is where the heck is antimony on this thing? I think it's right there. That's the pnictogens. Nitrogen, phosphorus, arsenic, antimony. What is that? 121.760. I'm covering it with my thumb. 121.760. 121. I forgot what I said already. 0.760. This is why I can't play Texas Hold'em, right? One of my buddies is a professional poker player. He just plays Texas Hold'em. Makes a living from doing that. I'll play against him. I'll look at my 2 cards and then put it down, and they promptly forget what they were. So the whole game, I keep looking at it. He's looking at me. He's like, why do you keep looking at your cards? You know, he thinks I'm thinking and trying to figure things out. I'm like, no, I just forgot what they were. I don't remember. Like, 2 jacks. All right, is that good or bad? So we can cancel out some units here. Milligrams of antimony, grams of antimony to moles. And now I'm in the hub. I can go from moles to number of atoms using Avogadro's number. So I'm taking last video's concept, the mole concept, and Avogadro's constant, and combining it with molar mass. So for 1 mole of anything, there's 6.022 times 10 to the 23rd of those particles. 6.022 times 10 to the 23rd atoms. So we happen to be dealing with atoms of an element. We'll do with molecules for a compound or formula units of a compound in a little bit. Moles cancels out, leaving us atoms. We should always end up in the upper right-hand corner with the units we're after. Check, 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 check. Everything works out beautifully. Now it's all multiplication division. I got 2 significant digits there. Metric conversions are exact. I got 6 significant digits in my molar mass. We got 4 in our Avogadro's number, so we're limited to the 2. And if we needed more, we could add more to Avogadro's number if we had to, right? Because we don't want Avogadro's number to limit us unless we have to. So to 2 significant digits, I get 2.0 vertical dash line 77 times 10 to the 20th. Now that's a lot of atoms of antimony. 42 milligrams doesn't seem like a lot. There's like 2.1 when we round it times 10 to the 20th atoms of antimony. It's an inconceivably huge number. So that rounds up to 2.1 times 10 to the 20th atoms of antimony. Boop. Pretty easy, right? Well, let's bring it up a notch. Let's do compounds and molecules. You are more often not going to be using pure elements, right? You're going to be using compounds or polyatomic ions or substance, which is multiple atoms of different types of elements combined together. So we can apply the molecular mass, which would be the mass of 1 molecule or 1 formula unit if it's an ionic compound, and that'd be atomic mass units per molecule or formula unit. But if you're dealing with mole quantities, it's grams per mole, right? That'd be the molar mass. So things like water, 2 hydrogens, 1 oxygen, sodium sulfate, 2 sodiums, 1 sulfur, 4 oxygens, etc. You can't just look at the periodic table because it's not on there, right? That's just elements. So how do we do the molar mass for a non-element species? Well, just break it down. Break down. All right. And just count the number of moles of each element and just add them together. That's all you do. Right? It takes a while, but you're going to do this all the time. It will be an addition problem. Like, for example, here, we would just take hydrogen plus oxygen. We have 2 moles of hydrogen, so I take 1.00794 plus 1.00794 plus 15.9994. I just take the values off of here. And you can summarize that and just go 2 times 1.00794 plus 15.994. But fundamentally, it is an addition problem. Here, I take sodium, right, plus sulfur, plus oxygen, plus oxygen, plus oxygen, plus oxygen. Or 2 times sodium plus 1 times sulfur plus 4 times oxygen. Since it's an addition problem, you're limited by the fewest number of decimal places. So take a look at all the elements in that particular compound, find the number of decimal places of each one, and the one with the fewest number of decimal places is the one that's going to limit your final molar mass that you calculate. So you just look through, oh, I got 4 decimal places in that one, 5 in that one, 3 in that one, so boop, good to 3 decimal places in my final answer. So you can just do it real quick. You never need to show me your work for this. If you have a different professor, maybe they do, but you can just pop it on your calculator. I can just take 1.00794 times 2 plus 15.9994 is 18.01528, right? Good to 4 decimal places because hydrogen's 5 decimals and oxygen's 4. So you can pop that out real quick. Let's do one that's a little more complicated. Let's take a look at ammonium sulfide. It's an ionic compound, so we're looking at the formula unit of it. So this would be the formula mass, by the way. It's molar mass, but specifically a formula mass. Well, let's break it down. How many moles of nitrogen? If I had 1 mole of this, how many moles of nitrogen? I'd have 2 times 1. Remember, take the number outside the parentheses times the number, the subscript inside. So that's 2 moles of nitrogen. 4 times 2 is 8. 8 moles of hydrogen. That's an ugly looking hydrogen. And 1 mole of sulfur. So break it down into its individual element components. How many moles of each element? And then look on the periodic table. So if you look up nitrogen, nitrogen is 14.0067, good to 4 decimal places, right? Hydrogen, you probably have memorized by now, James Bond, right? 1.00794. That's good to 5 decimal places. Sulfur, let's find sulfur. That's a chalcogen, right? Or chalcogen, depending on how you do it. Sulfur's 32, on my periodic table, 32.066. That's good to 3 decimal places. So all I'm going to do is take 2 times 14.0067 plus 8 times 1.00794 plus 1 times 32.066. The 2, the 8, and the 1 are exact numbers, right? So this is treated literally, you're going 14.0067 plus 14.067 plus 32.066 plus that 8 times. So like I said, fundamentally, it's an addition problem. 4 decimal places, 5, 3. So this limits to 3 decimal places. So that will limit you. You do not need to show your work. Just literally pop it out. 14.0067 times 2 plus 1.00794 times 8 plus 32.066. Boop! Good to 3 decimal places. And when you do it, let's see what you get. I get 68.142. I'm going to pop my vertical dash line there because that's my 3rd decimal limited by the sulfur, correct? 68.14292 grams of ammonium sulfide per mole of ammonium sulfide. That's a conversion factor between grams of any substance and moles of any substance. It's molar mass, so we're just not doing elements now, we're doing more complicated compounds. Now that would round to 68.143 grams per mole of ammonium sulfide. We are never going to use the rounded molar masses, so I don't even bother. Unless that's what the question is. What's the molar mass? Then you could round it, correct? But I'm not going to round that because usually the molar mass is just something we calculate in order to do another step in a larger picture, a longer unit line equation. Because remember, we always want to, we're measuring things and usually masses and volumes in lab. We need to convert that to moles to theoretically do problems, right? Which we'll do in a later chapter. Very simple to do. So let's actually do a more complicated problem using this molar mass. Let's put it up on the board, see how you do. Let's put it all together, baby. If you can do this next problem, you're good for my exam. Here you go, my friends. I love this problem. How many hydrogen atoms are there in 15 grams? That's not an exact number, it's measured, right? So that'll be 2 sig figs of ammonium sulfide. Now, I could have twisted this up and said, well, how many ammonium ions, or how many nitrogen atoms, how many sulfide ions. I could take any portion of this, it's an ugly looking 4, and ask for that, right? So I love if I do like 3 versions of a quiz. One, I'd ask for hydrogen atoms. The second one, I do the same problem but ask for nitrogen atoms. and a third one maybe sulfide ions, right? We can break this down. Remember, a chemical formula is a conversion factor between that compound and any element within it. So we want to know how many hydrogen atoms are in 15 grams of this. We obviously need to get to moles. So here's our game plan. We're starting with grams of ammonium sulfide. We want to get to atoms of hydrogen. So here's our starting point of our journey. There's our ending point. So if I can get to moles of ammonium sulfide, I can break it down. There's 8 atoms of hydrogen, or 8 moles of hydrogen per mole of that. So let's get to moles of this and then break it down into moles of hydrogen. And then once we're in moles of hydrogen, we can use Avogadro's number to get to atoms of hydrogen. It's actually 2 ways we could do this. I think this is the simplest way. So I got to get from grams to moles, right? That's molar mass of any substance. So I can get to moles of ammonium sulfide quite readily, and that would use molar mass. And if you can do this without the game plan, just do the game plan in your head. You never have to waste your time on an exam doing this, But if you're working on homework and you're new at this stuff, it might help just to go, I'm starting here, ending here. How do I connect these? Oh, I need Avogadro's number. I need molar mass. I need a metric conversion. I need an English to metric conversion. And you find those items. So once I'm in moles of the whole substance, I can go to moles of any portion of that substance, right? So you see the 2 times 4? We did this when we calculated the molar mass. I can go to moles of hydrogen using the chemical formula as my conversion factor. Right? So step 1, step 2. Once I'm in moles of anything, I can go to particles of that, correct? So using this, I can use Avogadro's constant, which is that capital N sub capital A constant, which I provide for you. Okay, I'll provide you the periodic table to calculate that. You should be able to figure things out from the chemical formula. And off we go, my friends. Let's do it. How many grams we got? 15? We got 15 grams of our starting material. Let's go to moles. Now, we already calculated the molar mass earlier, so let's just do it again. Again, it's just 2 times 14.0067 plus 8 times 1.00794 plus 1 times 32.066, limited to 3 decimal places. Right, so that was that 68.142 vertical dash line 92 grams of ammonium sulfide per mole. Check, step number 1 complete. And then if you like to cancel out your units, you can cancel out the grams of ammonium sulfide. I like to do that still after over 30 years of doing this stuff, because I like to make sure that they all cancel out. And the only thing left is the unit I'm after of the species that I'm after, right? Because I got different things. I'm talking hydrogen, ammonium sulfide. So if you got moles, is that moles of ammonium sulfide? Is that moles of hydrogen? Is that moles of moles of what? Remember, you can't just say, hey, go get me 2.5 dozen. Doesn't mean anything to me. Now we're in moles of that. We can break it down and go to moles of hydrogen. So for every mole of ammonium sulfide, there are 8 moles of hydrogen, right? 2 times 4 is 8. So we've gone from moles of the compound to moles of an individual portion of that compound. This is an exact conversion, by the way, because it comes from a chemical formula. That's going to be 5 sig figs. That's going to be 2, probably going to be limited by 2. But double check, you're not always limited by the first number. Watch out for that. Check. Step number 2 complete. Now we can use Avogadro's constant. So for every mole of hydrogen, we're going to have to squish this one in there. We've got 6.022 times 10 to the 23rd atoms of hydrogen. Wada bing, wada boom. Moles of hydrogen goes bye-bye, and I'm left with the unit that I'm after, correct? That's got 4 sig figs, exacts, 5, limited to 2 significant digits. So if you punch this out, take 15 divided by 68.14292 times 1. You don't have to do that one. Times 8 divided by 1. Do that in your head. Times 6.022 times 10 to the 23rd divided by 1. Right? So I get 1.0 vertical dash line because of the 2 sig figs from the mass I originally did. 1.060 times 10 to the 24th atoms of hydrogen. Or you could say hydrogen atoms. Doesn't matter. Let's look. That's going to round up to 1.1 times 10 to the 24th. Give me that arrow. 1.1 times 10 to the 24th. Atoms of element number 1. Not too bad, right? As long as you think about it. So the only new concepts here is Avogadro's constant uses a conversion factor to get from particles to moles or moles to particles. And this concept of molar mass that allows you to get from moles to mass, to grams. Put them together, you can do just about any problem you want. And I can work it forward or backwards. They're all the same. That's why you got to do your homework so you can see all the different ways of doing it. You guys rock. We're done with this journey. We're going to move on to something else now.